All right, greetings and welcome to the Chapter 12, One Day, One Assignment. These problems right here are due tomorrow on Chapter 12. And if you'd like to follow along, we're on page number 482 in your textbook. There are 6 different types of solids that we're going to talk about in this chapter: metallic, ionic, covalent network, molecular solids, polymers, and nanomaterials, 5 of which I'll do during this lecture. All are outlined in Chapter 12 of your textbook, and we will show you pictures of the textbook pages that we have displayed in class as we go along. First of all, there are 2 different types or formations of each of these solids. There are crystalline formations, which have ordered and repeating patterns, and there are amorphous solids that are like liquids frozen in place that don't have very good organization. If you look on page number 482 of your textbook, you can recognize solid substances have a nice organized repeating pattern here. Some ionic substances have nice organized repeating patterns. Here's a covalent network solid with a nice organized repeating pattern, and a molecular solid that's also fairly organized and repeating pattern as well. You can move that back. Those are called crystalline substances. NaCl is an example. SO2, known as quartz. Diamond, form of carbon, very organized repeating pattern. And then amorphous or frozen in place solids would be things like frozen lava, known as obsidian. From your Minecraft days, remember that it takes lots of hits from your chopper to get the obsidian. Don't you have to have a diamond pick to get that? Yeah, diamond pick to get the obsidian. Glass, like the kind of glass that you look through, that's frozen in space. And then rubber is another example of rubber bands of an amorphous solid. All right, let's look at details for each one of these. First one, metallic solids. Metallic solids are things that are good conductors. They're malleable, they're ductile, they're rich in electrons, and they have what's called a mobile SEA of delocalized electrons. And if you go to page number 495, page 495, it has a really nice picture of this metal ions with a mobile sea of electrons. Page 495 right here, you can see the mobile sea of electrons, and it's those mobile electrons, those movable electrons, that allow it to be a really good conductor of electricity. And then it also makes it so it can have a lot of shininess to it. The shininess is because the electrons, when struck by light, bless you, bounce back at you. And this is called luster. Turn to your neighbor and say luster 3 times fast. Ready? How do we know this? How do we know these metallic pieces are bonded together in a regular organized pattern? Well, it has to do with this thing right up here called X-ray diffraction. And so if you think back, you're a little bit dangerous in this world without knowing it. Think back to Chapter 6. Way back in Chapter 6, you learned about this thing called an electromagnetic spectrum. Remember this chart right here? Or maybe you remember this chart here on the back better. And this is something that you learn in physics class that you might not know right now, but if you take electromagnetic radiation, like for example visible light, and you shine that light through a very small opening, like for example the space between these 2 pieces of paper, then what happens is that electromagnetic radiation, that's not a particle, not a wave, but a mix of the 2, some people call them a wavicle, is bent or diffracted. And when it does that, it makes a regular repeating pattern after that if you put a screen behind it. This is called a slit or a double slit experiment. And depending on the size of the wavelength of that radiation, you need different sizes of the slit to make sure that it can go and show that regular repeating pattern. Turns out, and this happens to be on page 486 of your textbook. You want to show that page up here for just a second, please. Page 486. This regular repeating pattern is the way that we can figure out what different substances are made of. And I have a quick video for you here of a guest speaker that'll describe how this X-ray diffraction works. Now, it's not very loud, and those of you that are at home, I'll put the link on the Schoology page if you want to watch it yourself. But we'll watch as he describes how X-rays with really, really, really small wavelengths, can you tell that they're smaller right here wavelength-wise than visible light, can be used to go between the really small area where the spheres that represent an organized pattern of crystalline substances are. Ready, set, go.
The idea then was to take a crystalline solid, something that has lots of planes of atoms, and use each plane of atom as kind of like a slit in a double slit experiment. You take a beam of X-rays from an X-ray tube, which accelerates electrons up to some voltage, and smashes them into a metal, which makes X-rays. Then you can make a beam of X-rays by passing it through a lead screen with a small hole in it, because lead is pretty good at stopping X-rays where there's lead. So now you have a beam, and you hit this crystalline solid, and the pattern of scattering off of this crystalline solid makes really interesting stuff. You normally get this central spot here in this pattern from the beam itself, but then you get this array of dots of constructive interference from scattered X-rays. This is called sometimes X-ray diffraction, although it's not really the best term.
So it's this scattering right here, or this organized collection of these little spots that you could measure the distances between, and then from that you could infer what the crystalline structure looks like. So that's how we know that there are these types of structures, or as you see up on the screen up here, these types of structures that make up a particular solid. X-ray diffraction, super useful tool in deciding what type of organization of solids we have. So that's metallic solids. Let's move on from there and let's talk about the second kind of solids. These are called ionic solids. This is on page 499 of your textbook if you're following along. Ionic solids are ones you actually learned about way back in chapter 2. Ionic solids are metals and nonmetals. They're stuck together pretty good. And they actually kind of break the rules of what we've been talking about in chapter 11. Because in chapter 11 we talked about how things that have melting points or boiling points are held together by intermolecular forces called London dispersion forces, dipole-dipole forces, and hydrogen bonding. Well, in ionic substances, when you want to melt them or boil them, you actually have to break or disturb the intramolecular force called ionic bonds. And it's difficult to do. That's why those things like salt, NaCl, have a really high melting point. I mean, it takes like 800 degrees Celsius to melt NaCl. Take a periodic table for a second right now, and look on table 12.3, and on your periodic table find the element lithium. Find lithium, point to it, show a neighbor. Find lithium, point to it, show a neighbor. Find lithium, point to it, show a neighbor. Find lithium? Okay, now look at the melting point for lithium fluoride. And now let's see if you can find the pattern. Find sodium on the periodic table. Where's sodium as compared to lithium? Now find potassium. Now find rubidium. Okay, do you see the pattern? Where are those located? Now look at the melting point. See if you can recognize a pattern. Turn to your neighbor and tell them the correlation between position on the periodic table and melting point of those substances. So as you look on the periodic table, you can see that lithium, sodium, potassium, and rubidium go down the periodic table in group 1, and the melting point also goes down, or is reduced as well. You actually know why this happens, although you might not remember it from chapter 7. In chapter 7, you talked about some trends on the periodic table, and as you go down a group or a family, the size of the atom increases. And since the distance between the two atoms then would get larger, as you go down the group of the family. The separation would be more, and therefore the melting point gets lower because it's easier to separate those two ionic substances. Okay, ionic bonds have no conductivity in solids, but once they're molten or melted, then they conduct electricity. They have really high melting points, and we looked at the table on page 498. Next type of solid are called molecular solids. Molecular solids are ones we've been talking about in chapter 11. Molecular solids are ones that are held together by London dispersion forces, dipole-dipole forces, or hydrogen bonding forces, depending on what they are. On the screen right here, I've got two molecular substances you might know the name of, C12H22O11. It's the stuff you put in your cookies, and it's in all kinds of candies. What's the name of C12H22O11 in slang terms? That's sugar, right? So that's sucrose. Sucroses are held together by sucroses with intermolecular forces. They're not nearly as strong as those ionic bonded forces, and so they melt at a much lower temperature. As a matter of fact, I think you can liquefy sugar like on your stove at home. Have you ever melted sugar before? Or maybe burned it? I mean, you can do that with regular stove temperatures, so maybe like 250 Fahrenheit or something like that, which is, not that hot as compared to what you need for energy to break ionic bonds. So weaker intermolecular forces will change the phase for those guys. The next kind of substance is called covalent network. Covalent network substances are made of atoms, and they're large networks of covalently bonded atoms. Because covalent bonds are much stronger than intermolecular forces, these solids are much harder and have much higher melting points than molecular substances. Some examples of these would be carbon in the form of diamond, or carbon in the form of graphite, or silicon just in the form of silicon, germanium in the form of germanium, SiO2 in the form of quartz, SiC, Bn. Be a good test taker here and anticipate a question that is like, classify these as being covalent network, and then you'll have to select from a list of like 5. Notice on the periodic table, where's the element carbon? Where's the element silicon? Where's the element germanium? Can you find a pattern on the periodic table? Where are they located? So notice that those type of covalent network substances are in one area of the periodic table. They call diamond and graphite allotropes of one another because they're just different organizations of each other. Now, if I had a chair, I could show you, but I have 3-dimensional models of each. This is a 3-dimensional model of the allotrope called diamond. You can see it's a regular repeating pattern, and it actually forms a tetrahedral. And if you want to put page number 503 up on the screen, you can actually see the picture of diamond in like a tetrahedral shape, which makes it super strong. And then you can see graphite right here. Here's a 3-dimensional structure of graphite. Graphite is actually the stuff that makes up your pencil lead. And what happens is these bonded hexagons are stuck together by covalent network bonds, but the layers of graphite are stuck together by dispersion forces. So it's like really easy to take an entire layer of the graphite off, and then that rubs onto your paper, and that's what makes your mark from your pencil. So graphite guys right here are the ones that make up lubricants or things that make up pencil lead. Now, one of the cool things about these covalent network solids is that many of them are in a class of substances called semiconductors. Semiconductors are substances that sort of conduct electricity, which makes them super valuable in your world today, in my world today, because without semiconductors, you wouldn't have any electronic devices. You wouldn't have your phone, you wouldn't have a computer, you wouldn't even have a car, because everything works based on these computerized pieces, and semiconductors are the heart of them. You know enough chemistry to be a tiny bit dangerous in the world of understanding how semiconductors work. Look on page number 504 of your book, please. 504. You can put this little picture up on the screen. And then you can go ahead and remove it again because some people are still writing down some notes. And semiconductors made of silicon or germanium, well, they work kind of like this. Find silicon on your periodic table. Point to it. Show your neighbor where silicon is. Remember silicon? It's the crazy criminal. What's the crazy criminal called? Silicon, yeah. Okay. So the silicon, how many valence electrons does silicon have? 4 valence electrons. You learned this back in chapter 6. 1s2, 2s2, 2p6, right? And we could show the valence electrons like this. 3s2, 3p2. Remember these orbitals? And then you learned in chapter 9 that you actually took these 2 orbitals and hybridized them together so they'd have the same kind of energy. All 4 electrons would be lined up in a row and each could go out and form a bond. That's sort of true. That's one good way to represent it. Another way to represent it was actually taught to you a little bit. Remember when the professor was here one day and he talked to you for the entire hour? You remember that? You remember that? Yeah. Okay. He tried to introduce to you another way of representing these electrons around molecules. So you can be dangerous enough to know how this works. Here's the second way to represent it. I want to put that book up on the screen again. You can take those 4 electrons, that are valence electrons, and put them into something that's called a molecular orbital. All 4 electrons can go in this particular molecular orbital called a valence band. All 4 of them can go in there because they're all of almost equal energy. Then there's an energy space, and there's another orbital up here that has 0 electrons. And there's an energy distance between the 2, and it has a fancy name. What's the fancy name of the energy distance between the 2? It's called a band gap, right? Now, if there's a huge, huge band gap between where the electrons are and where the electrons aren't, then the electrons can't move between and therefore can't conduct electricity. And so we call that substance an insulator. Call it an insulator. If the distance in between right here is very, 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 very close, then electrons can easily go between the full and the empty band of electrons, and it can conduct electricity. But if the distance is Goldilocks, you guys know who Goldilocks is? Not too hot, not too cold, but then only some electrons will jump from the valence band to the conduction band, and you get a semiconductor, because it only sort of conducts electricity. Silicon happens to be one of those substances. So does germanium, and a few other substances that are over right near that group 14 of the periodic table. Now, you can change the semiconductors so you can manipulate them, and the basis of the semiconductor is that it's either an on or an off switch. For you computer people that will eventually program, you usually know that on or off is either a 1 or a 0. On or off. And you can take a whole bunch of these semiconductors, put them in a really, 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 really small space called a microchip, and then you can have lots of ons and offs going at the same time. By lots, I mean like billions. Lots of them. And then that can be organized in a certain pattern to be like the character A on your computer screen. You can manipulate these by doing what's called doping. Doping the semiconductor. Yeah, it's actually called doping. Turn to your neighbor and say doping 3 times fast. Ready, go. You can dope the semiconductor by exchanging one of the atoms with one that has either one more or one less electron than what the normal semiconductor has. And when you dope it, then you can control that electron a little bit better to make it be flowing an electron on or not flowing an electron on. So let's see if we can do an example. Let's take silicon as an example of a semiconductor. And let's take like one atom out of every 10 million out of that semiconductor, and let's put a different atom in its place that has one more valence electron. Look on your periodic table, find silicon, find an atom that's nearby that has one more valence electron. What's the name of that atom? So you could dope it with an atom of phosphorus every 10 millionth atom or so, have one more electron, and then you would have what's called a negative type semiconductor. negative type semiconductor. They don't call it negative type. Guess what they call it? N-type semiconductor, because it has a negative charge that can easily go between the band gap and conduct the electricity, be an on or an off. You could do the opposite of that as well and make a positive conducting happen by doping it with an atom that has one less electron. So let's pick a different semiconductor. Let's look at germanium. Find germanium on your periodic table. Okay? Let's dope it with an atom that has one less electron than germanium in its valence shell. What atom could you choose? Gallium. Okay? And so since you have one less electron, you have one less electron in this valence band right here. And remember, minus a minus. And so you call it a positive type semiconductor. But it's not called that. What is it called? It's called a P-type semiconductor. Exactly right. So you can have one of those two types that you can control better, and then those types are the ones that can be your ons or offs in your semiconductor world. Last type of solid to talk about today, polymers. Poly stands for many, and then mer stands for parts, so it's many parts joined together to make a long, long, long chain molecule. Many polymers are plastics, and an example is on page 509 of your textbook, where we can take the monomer known as ethene or ethylene. See, it has two carbons, two hydrogens, and a double bond right here. Break one of the bonds, and then use that to connect more of these CH2s together. And then you get a long chain of CHs, long meaning like millions of them together. And then you get, it's gone now. Oh, you have to move that table again. I'm sorry, move that book again. You get a long chain. Oh, it's right down here. It's called polyethylene. Polyethylene is a plastic that's used to make like milk jugs or water bottles. That's a polymer. Got it? Turn to page 510. And on that page are a whole bunch of different polymers right here. And in your notes, pick three. Pick three names of different types of polymers and put down one of their uses. If you don't want to pick, I'll pick three for you. Here's one that I picked. I picked polystyrene. You don't have to draw the structure, but you can notice it's got a benzene ring in it. Polystyrene is something that was used to make styrofoam. Here's another one to pick about polyvinyl chloride, PVC. You can see it's just like the monomers that we talked about for polyethylene, except it's got a chloride that's in there. This is used in like PVC piping. Pick one more. Here's one that I like right here. Nylon. Nylon is a polymer that's used to make fishing line. Did you pick three? Did you pick three? Put three in there? Now there's two different ways that your book talks about for making these polymers, and we'll put both down in our notes. The first method of making the polymer is called addition polymerization. This is when you add two things together. This is like the one I showed you before, polyethylene. Take and open up the double bond right here, connect it together with another one that opens the double bond, and you get many of those in a row, and you get a polyethylene polymer. That's called addition, because you add them together. Second type of polymer is a condensation polymer. This is where you would join two molecules together, and you would form one large one and eliminate a small molecule. Eliminate a small molecule. An example of this type of polymerization is written on your notes. Nylon is one of those. And you can see in this one, you would take the H from here, the OH from here, pull those apart and eliminate that small molecule called water, and then you would stick the N and the C together. So you'd get an NHCO, 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 and just put those together in a super long chain and make a long polymer. Tomorrow, we'll continue our talk of different types of solids with one more in nanomaterials. But for tonight, your homework problems are the 9, 10, 12, 69, 70, 77, and 82 from Chapter 12. Thanks for tuning in. Best of luck on your solid homework.
Hehehe